Nvidia just released a checkpoint that changes everything you know about model sizing. You can run a 30 billion parameter model, a 23 billion parameter model, or a 12 billion parameter model from that single file. The problem is that most engineers still think they must choose one fixed size and live with its limitations forever. By the end of this video, you will understand how to slice that single checkpoint dynamically based on query complexity without any retraining. For years, the engineering trade-off has been brutal. You either deploy a massive model that consumes all your memory and costs a fortune to run, or you deploy a tiny model that is cheap but fails on complex reasoning tasks. Traditional solutions involve training separate models for each size and maintaining a cascade system. This means loading a small model, checking if it can solve the query, and if not, loading a larger one. This approach creates significant latency overhead because the system must constantly load and unload different weight sets. It is inefficient and expensive. The new approach from Nvidia, known as Nemotron Elastic, eliminates the need for multiple checkpoints entirely. The core innovation is a zero-shot slicing mechanism that treats the entire 30 billion parameter checkpoint as a single contiguous tensor. Inside this tensor, the model contains nested submodels of different sizes. The 12 billion parameter version, the 23 billion parameter version, and the 30 billion parameter version all share the same latent space. They do not exist as separate files. They exist as different activation patterns within the same data structure. Here is the thing that makes this architecture unique. In standard model compression, you prune weights and lose information. In this elastic framework, the model is end-to-end trained with a specific router mechanism embedded within the architecture itself. This router uses hybrid Mamba-Attention structures and group-aware state space models to determine which parameter subsets are required for a given input. When a simple query arrives, the internal gating thresholds activate only the 12 billion parameter subset. When a complex reasoning task arrives, the system seamlessly expands to utilize the 23 billion or 30 billion parameter subsets. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This dynamic allocation happens without any external classifier or routing logic introducing latency. The inference engine skips computation for inactive layers instantly. Because the weights are already loaded in memory as a single block, there is no overhead associated with swapping files. The system adjusts compute utilization by simply changing the inference context window or batch size. This allows for immediate scaling of resources based on real-time needs. The efficiency gains are not theoretical. In production environments, this approach has demonstrated a 360 times cost reduction compared to training and maintaining separate models for each size. When you compare it to standard compression techniques, you see a 7 times improvement in efficiency. The memory footprint remains constant regardless of which model size is active. This means your peak VRAM requirements for mixed workloads can drop by up to 60%. You do not need to provision for the worst-case scenario anymore. However, implementing this in a real production pipeline requires a specific strategy. You must treat the checkpoint as a single entity and configure the inference engine to handle conditional masking. The critical insight here is that the model does not know which size to use until it processes the query. The router evaluates the complexity of the input and activates the appropriate internal pathways. This means the system can handle a mix of simple and complex queries in the same batch, optimizing the overall throughput. There is a primary failure mode you must watch for. If the query complexity is misaligned with the model's internal gating thresholds, the system might trigger the 30 billion parameter model for a trivial task. This wastes compute and defeats the purpose of the elastic scaling. To prevent this, you need to implement a confidence calibration layer in your pipeline. This layer enforces a minimum complexity threshold before allowing the larger parameter subsets to activate. It acts as a guardrail, ensuring that the system only scales up when the query truly demands it. This shift in architecture changes the skill set required for modern AI engineering. You are no longer just selecting a model, you are now tuning the inference process. You must optimize the trade-off between the marginal cost of activating extra parameters and the diminishing returns in reasoning quality for specific domain queries. The career focus moves from model selection to inference tuning. You need to understand the latency overheads of the routing mechanism and validate them against the theoretical efficiency gains before adopting this strategy. Consider the practical implications for a junior engineer. In the past, you would spend weeks training a smaller model to fit your budget or waiting for a larger model to finish training. Now, you can deploy the parent checkpoint and let the system handle the rest. You configure the routing logic and the calibration layer, and the system adapts to the workload automatically. This reduces the operational burden significantly and allows you to focus on improving the quality of your data and the logic of your applications. The technology relies on the assumption that the internal attention patterns can be trusted to route queries correctly. This is why the end-to-end training is so critical. The router learns to recognize complexity signals that a human might not be able to specify explicitly. It discovers the patterns that separate simple tasks from complex reasoning tasks. This learned behavior is what allows the zero-shot slicing to work without retraining. As you move forward with this technology, remember that the flexibility comes with responsibility. You must monitor the routing decisions closely. If you see the large model being triggered too often, you may need to adjust the calibration thresholds. If the small model is failing too frequently, you might need to tune the complexity detection logic. The system is powerful, but it requires careful tuning to perform optimally in your specific environment. This represents a fundamental shift in how we think about model deployment. We are moving away from static, one-size-fits-all solutions toward dynamic, adaptive systems that respond to the needs of the user in real time. The future of AI infrastructure is not about having more models. It is about having smarter ways to use the models we already have. By mastering this elastic architecture, you position yourself at the forefront of production-grade development. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.